Video here for lesson number 4. In today's lesson, we're going to take what we looked at in the first 3 lessons and look at it in a kind of different lens. So we're going to look at this as a recursively defined sequence instead of a explicitly defined sequence, which is what we did in lessons 2 and 3. We're going to look at the same exact patterns, the same exact sequences, but we'll be able to define them just a little bit differently. So if we were in class, the opening exercise is a review of what you should have remembered how to do from lessons 2 and 3. So I'd say go ahead, try the opening exercise. So pause the video, try it, see how you do. All right, so hopefully you paused the video and tried these two. So the first one would be an example of an arithmetic sequence. I know that because it has a plus sign. A plus and minus is telling us that we're going up by a common difference. So the common difference in this case is 4, and the first term of the sequence would wind up being 6. So the sequence would start at 6, and then every single term would be 4 more than the previous term. The second example here, b sub n, is a geometric sequence. I know it's geometric because there's multiplication. The common ratio in this case is 2, and the first term is going to be 7. So essentially this opening exercise is just making sure that you know what the parts are of the explicit formulas. These are the 2 explicit formulas that we need to know how to use, the one for arithmetic and geometric. So let's take a look at another sequence. So everything we've done, like we said here, has been an explicit formula. Explicit formula, what that means is when you plug in a value for the variable, you're going to get the actual term that you want. So if I want to find the 15th term of the sequence, I'm going to plug in 15, and I'm going to get the 15th term of the sequence. Not all sequences can be shown explicitly. Some of them have to be shown recursively. What recursive means is to find the 15th term, you would need to know the 14th term. So the pattern of the sequence is defined in a way where the previous term is needed to find the next term. So let's begin the lesson with looking at familiar sequences we're used to seeing, right? And then we'll look at some of the more challenging ones towards the end. So in this first example, I have an arithmetic sequence. I see that the common difference is 3. So we are describing the sequence. Describing the sequence helps us start to think recursively. So we'd say that the sequence starts at 5, and each term is 3 more than the previous term. When you're describing a sequence, you want to describe it as if the person reading or you're explaining it to this person has no idea what the sequence of numbers is. So say, for instance, I said a sequence starts at 5 and each term is 3 more than the previous term. You should know then that the second term is 8, the next term is 11. I want to give you all the information here when describing. So the next 2 questions kind of give us an idea of how a recursive sequence is going to be written. So it says, how do we get from the 3rd term to the 4th term? So the 3rd term is 11, the 4th term is 14. We are going to add 3. Then says, how do we get from the 6th term to the 7th term? We would again add 3. So what we can see by these 2 questions is that no matter what, to get from one term to the next, I'm going to add 3. Now, we want to be able to define this for any term of the sequence, meaning I want to use variables. So if we know that any term of a sequence is a sub n, how would we represent the next term of the sequence? So if a sub n is our term, to get to the next term, we would add 1 to that n value. So the next term is a sub n plus 1. So when I'm writing a recursive formula for a sequence, I need 2 pieces. I need to first talk about where the sequence begins. So the first thing I'm going to put in my answer here for what the recursive sequence is what's the first term? The first term of the sequence was 5. I have to say where it begins. The second sentence, or the second thing that we're going to write here, is the rule. How do we get from one term to the next? So what we're going to say here is the next term is equal to the previous term plus 3. So notice I'm using the symbols for next term and current term, and then I'm just adding 3 to the current term to find the next term. Essentially, what I just wrote here in symbols is exactly what I wrote up here in this sentence. I'm just writing it in symbolic form using what we know about sequences. So our rule here for all of these is figuring out what the pattern is describing to us. What's the rule, right? So in number 2, instead of giving you the sequence, I'm giving you the recursively defined rules. So what this is saying is the first term is 2. That's the easy part. What this rule is saying, a sub n plus 1 is the next term, and I'm going to multiply 3 times the current term or the previous term. So we're going to say 3 times the previous term. Now, before we even do anything, I already know what type of sequence this is going to be. Because we're talking about multiplication, this is going to generate a geometric pattern. So it says explain the pattern of the sequence, right? So we'd say the sequence starts at 2, and each term is 3 times the previous term. Then it says write out the first 5 terms of the sequence. So we'd say a sub 1 is 2, a sub 2 is 6, a sub 3 is 18, a sub 4 is 54. I'm just getting these numbers by multiplying 3 times each term. So if I take 2 times 3, that makes 6. 6 times 3 makes 18. It's the same thing that we did in lesson 3, but now we're showing it using this new format, right? That's all it really is. It's just a new format. Now, because this is a geometric sequence, I can define it both recursively, that I've already shown, and explicitly. So if I gave you this in lesson 3 and I said write an explicit formula for this, you'd say, all right, it's a sub n is equal to the first term times the common ratio to the exponent n minus 1. This is defined explicitly, and then up top here in the opening part of this question, it's defined recursively. If you look, they look very different, but they're actually talking about and describing the same exact sequence. So let's take a look at another one. So we say, consider a sequence whose first term is 7 and follows this rule. So notice we have b sub n this time and b sub n minus 1. So this is always going to be the next term. Right, if I'm starting at b sub n minus 1, the next term is b sub n. So what they can do here in their recursive definitions, if they give you the recursive definition, is they can kind of mess you up a little bit by making the subscripts weird. Right, as long as you understand that the rule is defining the next term, you should be able to explain away your sequence. So what is your sequence telling us here? It's telling us that this is going to start at 7, and each term is 4 more than the previous. Since it's 4 more every time, we're adding 4 every single time. This is an example of an arithmetic sequence. Again, looking very different than what we did in lesson 2, but it's still an arithmetic sequence, just defined recursively. So if we want to find the first 5 terms of the sequence, we already know the first term is 7. To get from one term to the next, we're just going to add 4, so we'd have 11. To get to the third term, we'd add 4 again, we'd have 15. Add 4 again, we'd have 19, and then finally the 5th term would be 23. Now, because this is an arithmetic sequence, I not only can define it recursively, I can also define it explicitly. For example, if I didn't even give you any of this recursive stuff, and I just said, here's your sequence, write the explicit formula, you should know how to do that from lesson 2. So we'd say it's a sub n is equal to the first term plus the common difference, which was 4, times n minus 1. So notice we're showing it in both ways. So because we now know about recursive sequences, I now can start to define things using either one. So taking a look at the top of the next page, it says we can define an arithmetic sequence with a common difference of d as. There are two ways we can do this. We can define it explicitly by saying a sub n is equal to the first term a sub 1 plus the common difference times n minus 1. This we learned in lesson 2. What we're learning today is how to do this recursively whenever we define a recursive sequence, we have to state the first term. And then the next term of the sequence in an arithmetic sequence is going to be the previous term plus the common difference. Now, there are pros and cons to both. For example, if I wanted to find the 2000th term of an arithmetic sequence, I would never use a recursive definition, because the recursive definition would require me to know the previous term to find the next term. An explicit formula, I'd be able to just plug in the number 2000 and I'd be able to get my answer. Now, a recursive defined formula sometimes can be helpful when you're trying to create a full pattern, right? If I want to make 20 terms of a sequence, I want to use the recursive definition because it's a little bit easier. It's just telling you what to do to each term, right? Where the explicit one, you have to do a little bit more thinking, okay? Unfortunately, you need to know how to use both for this course. You can't just pick the one that you like best. We also learned about geometric sequences. So an explicitly defined formula for a geometric sequence would be a sub n is equal to the first term times the common ratio to the n minus 1. We learned this in lesson 3. If I want to define the same exact sequence recursively, I would first, again, state the first term. That's part of the recursive definition. And then I'd say the next term is equal to the previous term times the common ratio. So again, just like the arithmetic sequence, the explicit form of this is going to help you find the terms that are very high up, like the 10th term, 15th term. If I want to use or find all of the terms of the sequence, the recursive definition works best. So let's try a couple here. So on the bottom of the page here, page 15, there are 4 different sequences, and they're either arithmetic or geometric, meaning I can define them both recursively and explicitly. Okay, so I'd like you to try to do it both ways. So just try the first 2 on top. All right, one of them's arithmetic, one of them's geometric. So pause the video for a second and then try the next 2. All right, so welcome back. Hopefully you paused the video and tried these 2. I'm just going to talk through what I did for each one. So let's start with the first one, the 9, 1, -7, -15 sequence. So to define that recursively, I'd first start by stating the first term. So I'm saying a sub 1 equals 9. The next thing I'm going to say is, what's my rule? How do I get from one term to the next? So I'm going to say the next term of this sequence, a sub n plus 1, is equal to the previous term, a sub n minus 8. So I'm taking each term, and to get to the next term, I'm going to keep subtracting 8. To define that explicitly, I'm going to just use the rule I did in lesson 2. So I'd say a sub n is equal to the first term minus 8 minus n times n minus 1. For the second sequence here, I have a sub 1 equals 2. Again, I'm defining or stating the first term. Then I have to come up with a rule. How do I get from one term to the next? So to get from one term to the next, I'm going to multiply by 5. Remember, to find this number, this common ratio, I can always take the second term and divide it by the first term. So if you see that the pattern is geometric in nature, it's going up or down by a multiplier, but you're not sure what that multiplier is, you could always do that. Just to divide the numbers out. It makes it easier. Okay, if you can visually look at it and say, duh, Serbino, that's multiplied by 5. Why are you even saying this? Good for you. Give yourself a pat on the back, and hopefully you can get the fourth one here with doing your mental math tricks, right? So again, pause the video again, try these last two, see how you're doing. All right, welcome back. Let's check your work. So for that first sequence, 11, 17, 23, I notice it's arithmetic, so it's going up by a common difference. So the first term I'm defining as a sub 1 equals 11. And then the rule that I have here from getting from one term to the next is I'm adding 6 to the previous term. The explicit formula I put on the bottom there, 11 plus 6 times n minus 1. These on the explicit part should be easy at this point. I'm hoping easy at this point. For that last one, again, this one was a tough one to figure out what the common ratio was. If you thought about it for a minute, you might have been able to figure it out. Or if you just divide the second term by the first term, you notice it's 2/3. Do it again for the third term to the second term, then make sure it's geometric, and it is. And when you divide this, you do get a nasty decimal, 0.6 repeating. We don't want that decimal. We'd rather have the fraction. So if you're a decimal person, sucks. You have to use that fraction here. So when I define this recursively, I'm saying a sub 1 equals 162, and I'm saying each term is 2/3 times the previous term, so we're saying a sub n times 2/3. To define that explicitly, we have our explicit formula just like I did in lesson 3, the first term times that common ratio all to the n minus 1. At this point, if you're confused as to why we're doing these things both ways, it's because we can. It's not that one's giving you an advantage over the other. It's just two different ways we can do the same thing. Okay, so we just have to be able to define both. And you'll see here on the next page, we'll see a couple sequences that could not be defined arithmetically or geometrically. Therefore, we can't come up with an explicit formula for them. All right, let's do one more geometric sequence. Number 5 is a geometric sequence. So it says the amount of medicine initially given to a person is 120 milligrams. This is the initial amount. So that's the first term of the sequence, which they're defining as a sub 0. And it says every hour it has 15% less. So now we have to think, what do we multiply by 120 to get the amount left after 1 hour? I'll give you a clue. It's not 0.15. Remember in all of that work we did in our exponent chapter, it's always 1 minus whatever this percent rate is. So if I do 1 minus 0.15, I'm going to get 0.85. This number is my common ratio. That's what I'm going to multiply by one term to get to the next. So if I start with a sub 0 as my first term as 120, to get to the next term, I would take 120 and multiply 0.85. That's going to take 15% away from the previous term. If I do this again to find a sub 2, I'd say 120 times 0.85 times 0.85. So what you're going to notice here is the first term is 120, and the common ratio is 0.85. So if I define this recursively, I could say a sub 0 is equal to 120. And then we can say a sub n plus 1 is equal to a sub n times 0.85. The rule here is saying that the next term is equal to 0.85 times the previous term. That's literally what we did to find this pattern here. This is an example of a geometric sequence, so could you define this differently? I could define this just like I did in lesson 3 and use an explicit formula, but they did ask us for a recursive rule. So again, it all depends on what it says there in the problem. Now, number 6 is really the main reason why we even do this lesson at all. Because we can get away with knowing arithmetic and geometric sequences and doing their explicit formulas and never even saying the word recursive, but not all functions and not all sequences can be defined arithmetically or geometrically. Meaning not all of them have a nice, fun, explicit formula that can be used to find them. So sometimes it's just a pattern that's going to arise that we need to be able to use and define our terms of the sequence. Luckily, I'm never going to ask you to find like the 20th or 30th term because that would require you to find every single term to get there. So in this first example here of a non-arithmetic or geometric sequence, I noticed that they're giving us a bunch of information. They're giving us a starting point and they're giving us a rule. So the starting point says 4. So we know that this pattern starts at 4. And then here's my rule. So what that rule is saying is 2 times the previous term plus 3. So we're going to say it starts at 4, and then each term is 2 times the previous plus 3. So if I want to find the third term, I have to start with the first term. A sub 0 is 4. I know it's weird because you're putting a sub 0 there, but that's what they told us the first term was. So that's what we'll define our first term as. So if I want to find the second term, I'm going to plug in a sub 1. Now to find each term, you're going to multiply 2 times the previous term and add 3. So if I do 2 times 4, I get 8. And if I do 8 plus 3, I get 11. So again, what I did to find this answer is I did 2 times 4 plus 3. So if I want to find the third term of the sequence, a sub 2, I would have to say 2 times the previous term. Well, the previous term is 11. 2 times 11 is 22, plus 3 makes 25. Again, what I did to find that was 2 times 11 plus 3. That's the previous term. To find the third term of this, the fourth term of the sequence, a sub 3, which is what they wanted us to find anyway, we would say 2 times the previous term. 2 times 25 is 50, plus 3 is 53. Now, this particular pattern cannot be defined explicitly. There's no equation I can come up with here that's going to be an explicit formula because it's not geometric and it's not arithmetic. So the only real way that we could define this is using a recursive definition. Here's another one. So it says, here's a recursively defined sequence. A sub 1 equals 2. A sub n is equal to 3 times a sub n minus 1 plus n. Now notice they're using the n as an actual variable here. So when I want to find the second term, I'm going to say 3 times the previous term, 2, plus the term we're trying to find, the n value, 2. So that's 6 plus 2. That's going to give me 8. Let's try that again. If I want to find the third term of this sequence, I'm going to say 3 times the previous term, which was 8, plus the term I'm trying to find, 3. So if I do 3 times 8 plus 3, I wind up getting 27. Pause the video, see if you can use this pattern to find the fourth term. All right, so welcome back. Hopefully you did that, and we did 3 times 27 plus 4, and we found out that the next term, or the fourth term of the sequence, is 85. All right, so here's the point of the video where I'm going to say pause it, try your homework, come back to the video either later on today or tomorrow, and see what you get for your answers. Make sure that you're checking your answers as you're doing them, right? Make sure that if you have questions, you reach out to me so that we can make sure that we answer them, okay? So let's take a look at the homework assignment. Hopefully you've paused the video and you've come back here to check your answers. So in the first problem here, I'm giving you 4 different sequences. I'm asking you to classify it as arithmetic or geometric and write a recursively defined rule, right? Whenever we're writing a recursive rule, you need 2 parts. So look at your answers right now. If they are missing a sub 1 and you're not defining what that starting point is, it's not recursive. It's wrong. So for this first one, this is an arithmetic sequence. So we'll just put an A next there for arithmetic. I'm going to say a sub 1 equals 14. And I'm going to say any term is equal to the previous term plus 7. For the next one, this is an example of a geometric sequence. A geometric sequence because I see that there's a common ratio. The common ratio is times by 10. So if I want to define this recursively, I'd say a sub 1 is 4, and then I'd say any term is equal to the previous term times 10. All right, moving on to the next one, I notice that this next one is arithmetic. And the first term is negative 101. To get from one term to the next, we add 10. So I'll say the next term is equal to the previous term plus 10. The next one's geometric. I know that for sure because it goes from positive to negative. That's the only type of sequence we can get to do that. The other reason why we know it is because there's a common multiplier. Now, if you're not sure what that common ratio or common multiplier is, take the second term, negative 18, divide it by the first term, type that in your calculator, you're going to get 0.3 repeating, so we'll make that 1/3. So we can say the first term here is 54. To get from one term to the next term, we're going to multiply by negative 1/3, just like we did in the notes. Number 2 says, consider the recursive pattern where a sub 1 is 3. That's the first term. That's where I'm starting, and then every term after that is going to be 4 times the previous term. Remember, this is always going to represent next term. So what we could say is it's going to start at 3, and each term is 4 times the previous term. That's all this is asking us to do. All right, let's take a look at number 3. Number 3 gives us a graphed sequence. I know it's a graph sequence because all my points are not attached with a line, right? So they're jumping from one term to the next. So what we can say here is I can actually state my pattern. At 1, the value is at 2, so the sequence's value for the first term is 2. At 2, the sequence's value is 5. Still not sure if it's arithmetic or geometric yet. I'd have to look at the next term. So next term is 3, 8. So I noticed that there's a common difference here. I also noticed the points line up as a linear pattern, so that's going to give us a sequence that is arithmetic. So it says to write a recursive rule here. So to write a recursive rule, we always have to say what the starting point is, 2. To get from one term to the next, we're going to add 3. So I'm going to say to get from one term to the next term, I'm going to add 3. There is my recursive rule, and I am done. Hopefully this video helped. Hopefully you're keeping up with everything. Don't stress about it. I know you have lots of other stuff going on. Just try your best here to keep going with this unit, and we will get there. All right. Hopefully I see you guys soon.